So the goal is to understand certain singular SPDEs, so singular stochastic partial differential equations, from the viewpoint of semigroup theory, Markov processes, martingale problems, and so on. And this approach works for certain critical equations, and we get some results for supercritical equations, although mostly critical. But it needs structural assumptions, and it's not on the level of regularity structures. In particular, it doesn't apply to the singular SPDEs that you see in quantum field theory. And everything is joint work with Lukas Gräfner, who is a PhD student, and based on previous works with Gaussian-Gubinelli. So the motivation, or the model problem that we consider is, well, let's give 3 examples of equations we can look at. The first one is somehow a fractional variant of the Burger's equation associated to the KPZ equation. Where this here is space-time white noise. And U is on the one-dimensional space as a distribution. The second model problem, and here's a theta also. And I want to call this theta alpha. Is the surface quasi-geostrophic equation, which is somehow very similar. Let's first look at it like this. So this is an equation from, at the moment it's not stochastic, now this is an equation, for now we look at this. This will be a deterministic equation from fluid dynamics, which models the temperature of fluids in a certain regime. And it's very difficult to solve this equation. And I don't think there's any really good well-posedness theory for that model. And the best result that I know of would be to introduce on the right-hand side some dissipation. And in this case, in this case, the equation becomes critical, scaling invariant, and you do get well-posedness, but this was somehow a difficult result that was published some 15 years ago or so. And what this guy is doing is somehow taking energy out of the system. A priori, this thing is energy conserving. Now this thing is dissipating the energy, and this gives you the well-posedness, and somehow the 1/2 is critical. If you put here a bigger exponent of the Laplacian, then well-posedness is relatively easy with energy methods. If you put a smaller one, it is open, and the 1/2 is exactly the difficult one, where it still works. And what we're going to do is to do something where you don't dissipate energy. So, okay, we can put here also an alpha. And so this thing is dissipating energy. So now we add a second term, which is injecting energy exactly in such a way that formally somehow the energy that is injected by this one is dissipated exactly by that one, and so there's no dissipation, no injection of energy. You formally have energy conservation, except that the solution to this equation will have infinite energy for all times. And it's also, if alpha, so we cannot do alpha equal to 1/2, but alpha equal to 1/2 is also critical in the sense that the thing is scaling invariant for alpha equal to 1, and in that case, we would get well-posedness. And the third example is, sorry. Yeah, thanks. So these equations are very similar in a way, no? They're both somehow, you have like this exactly chosen so that, I mean, they match exactly here. Energy injection and dissipation is somehow both the same. And then you have some bilinear nonlinearity, which respects that energy that you have there. You could add, maybe as a comment, you could add here a different noise, which is somehow much, much nicer than the white noise. And you could also add some transport terms if you wanted. Maybe some. But this I will not really speak about. And the third example is a finite dimensional example. Which fits in the same framework on RD, where the divergence of B is 0. You could make the B time dependent, but for simplicity, I will not do that here. But then you could imagine the B to be the solution to some fluid dynamic equation, some stochastic Navier-Stokes equation or so, and then this is a particle that feels the force field somehow given by the velocity that is given by a stochastic Navier-Stokes equation with some diffusion. And if you take a stochastic Navier-Stokes equation that has a singular noise, then we know the solution will only be a generalized function. It will not be a function. So we would like to put a distribution here, and the result in this case would be that we can take B in, let's take Sobolev scale with minus gamma P, where gamma is bigger than, P is bigger than 2 divided by 1 minus gamma. And so the critical case. So in this case, things become supercritical in high dimensions, because the critical case in this case, again, scaling invariant case would be P equals D divided by 1 minus gamma. In dimensions bigger than 2, this can become supercritical. Okay, and everything somehow follows the same machinery. So everything falls into an abstract framework, and I try to explain the abstract framework, and I will not refer to these equations so much anymore, except maybe to this one on the basis of which I will develop the abstract framework. But then everything in the end will somehow be just some function spaces with respect to some measure, some L2 spaces. And it doesn't really have to be the same as in this setting. It just has to have the same features. Models have the same features.
So can you actually define what you mean by critical?
Yeah, so critical for this one or for any. So you rescale in some, let's give a meta definition. So you rescale in such a way that you look at the small time, small scale behavior, and in such a way that the linear part of the equation would remain scaling invariant. So here, this would mean you look at small times, and then you blow things up, right? So that the Brownian motion remains invariant. And then you look whether the norm, so this gives you a rescaled B here, right? If I do this rescaling, there will be somehow an epsilon, power of epsilon here and the power of epsilon here. And then you look whether in the function space that you're looking at, the norm of your rescaled B goes to 0 or blows up or stays the same. And in this case, I mean, if it's somehow sandwiched between these two, it would blow up. And here somehow you look whether there's a, I mean, in this case, because it's polynomial, the effectively will just come down to putting a factor in front of your nonlinearity at this rescaling, and then you see whether this factor, if you send the scaling to 0, goes to 0 or to infinity, or it stays invariant. Yeah, so let's see how we can do it in this setting. And again, somehow then everything is abstract. So we want to, the main thing that we do, the main thing that is new is develop these semigroups and the infinitesimal generators for these problems. So there will be two sides of the method. One is to develop a weak probabilistic solution theory for them, where you somehow make sense of this equation. You define somehow what you mean by a solution to this equation. I will address in a second why that can be difficult. And then a second step in which you want to prove that this notion of solution is unique, and this will be based on this link to the semigroups, because if you show that the notion of solution that you described, the law of that can be described in terms of the semigroups, then, well, it is unique because. And so the construction of these martingale solutions, of these weak solutions, is basically due to Goncalves-Jara and Gubinelli-Jara from a decade ago or so. And the new thing is this semigroup methods to recover now the uniqueness in that setting. Okay, so let's look at Burger's equation, this fractional Burger's equation for concreteness. So if we formally write down the generator, like the infinitesimal generator, the Markov operator attached to this U, then this is given by some L, which is equal to L0 plus G, which doesn't say anything, but so the L0 part corresponds to the linear part of the dynamics. And this part here corresponds to the nonlinear part of the dynamics. So this is somehow distinguishing these problems from quantum field theory kind of SPDEs, where you have reversible dynamics and everything is in this L0. Okay, sorry, one step back, we'll get there in a second. So in any case, so you split up into this L0, which is the linear generator, and then the nonlinear generator, which is G. And now you introduce a measure mu. And we work, so this measure mu is the law of the white noise on R. So this is now just, there's no time, just for a fixed time. The invariant measure is the law of the white noise on R. And this is the invariant measure for this fractional Burger's equation. And that's why I took exactly this 2 here and exactly the square root, exactly things to match out. And this corresponds to this formal conservation of energy. No? So you can perturb this a bit by adding additional terms like that, but here we won't do that. And then we can decompose, or in L2 mu, we have that the adjoint of L0 is L0, so it's symmetric, and G star is equal to minus G, so G is anti-symmetric. So, and this is different from the SPDEs in quantum field theory, where everything is somehow going into L0, and for us it's important to split off the singular part in something anti-symmetric or something sufficiently close to anti-symmetric. And well, so far everything is formal, but then we can actually consider the white noise, right? So this here is something that makes sense. L0, you can also somehow, the expression that you get there, you can make sense of it, it's defined rigorously. This thing here, this G, also you can make sense of it, but the problem is that this operator maps somehow to a nasty space. You cannot find a good domain for this operator. And to understand that, we need to do a little bit of regularity theory on this space now, on this L2 of mu. We have 2 unbounded operators. positive operators with which we measure regularity. The first one is this minus L0. Well, this we already discussed. The second one, to define that, we have to recall that by the chaos decomposition, by the isometry to Fock space of this Gaussian Hilbert space, we can represent L2 of mu as an orthogonal sum of these orthogonal spaces, these HNs. We don't really need to know anything about them at this point. Just need to know that we have this decomposition. And then we define the operator n, which is the number operator or Einstein-Uhlenbeck operator, which is defined on Hn. It's just Hn like this. As a multiplication operator. And then we also have, and that's important for us, that they commute these two operators. And then we define function spaces, H alpha beta, just as 1 minus L0 to the minus alpha half, 1 plus n to the minus beta, L to mu. And if one of these is negative, we would take a closure. And with a norm, the alpha half here is just because we imagine this L0 to be some sort of Laplacian, because we want the, and then somehow if you do the, I mean, 1 power of the Laplacian is like 1 derivative in the usual sense. So H1 means like half a power of the Laplacian, and that's somehow similar to here. That's why we do this alpha half. And for n, there's no link to some Laplacian, so that's why we just count powers normally there. And then we have an a priori estimate that says G of phi in H alpha, okay, I shouldn't call this alpha, gamma minus 3/2 alpha, beta minus 1/2. I'll comment on this in a second. Is bounded by H gamma, beta, sorry, and this I want to be 1 actually. If alpha is bigger than 1/2. Okay, this looks very technical. What does this say? So I have this alpha flying around here. The L0 is actually an L0 of alpha because I'm doing this fractional Burgers equation. And so for this given alpha, this will of course affect the definition of my operator L0. And if the alpha is bigger, the L0 will regularize more. If it's smaller, it will regularize less. And we see this here, right? So if the alpha is small, we lose a lot. We start with 1 regularity, 1 order of regularity with respect to L0. The upper is always L0 regularity. And we lose this 3/2 alpha. So if alpha is small, we lose a lot. If alpha is big, we lose little. And this only works if alpha is bigger than 1/2. So if alpha is not bigger than 1/2, you would get some different estimates, which are not, which at the end of the day, we cannot do anything. And so, and the beta here can be anything. So we plug in 1 order of regularity with respect to L0. We get something negative here. And well, this also always has to be negative. So I guess alpha has to be also less than. we also need 1 minus 3 over 2 alpha negative. Otherwise, this will not be true. So we always get something negative here. Okay. So what does this mean? Like, if you plug in a nice phi, the g of phi will always live in one of these weird distribution spaces, always in one of these spaces with negative regularity. And so therefore, we cannot find a domain for this operator, which is L0 plus g, because I mean, the nice functions are certainly not in there, because this thing will be of negative regularity. And L0 of phi for a nice function will be of positive regularity. And so therefore, there cannot be any cancellations. So the idea to build a domain for this operator of functions which are being mapped actually to elements of positive regularity is to use phis which have limited regularity so that there can be cancellations between this part and the L0 part. And we do this by effectively by solving a resolvent equation. Okay, maybe let's write this as a phrase. And this we get by solving 1 minus L phi is equal to psi for some right-hand side psi. If we could solve this equation, then by definition, somehow the L phi would be psi minus psi plus phi, and both of these would be of good regularity. So then the L of phi would be in the domain. Huh? And once we have the domain, then we will get a semigroup. And once we have the semigroup, we will get uniqueness of this Markov process. So basically the goal at this moment, this last part, I don't think I'll have time to really explain, but the goal is to construct this domain and then to construct a semigroup for this operator and to prove that on this domain, the operator has nice properties. Okay, so how do we do this? This here, somehow an infinite dimensional, but linear PDE, no? And okay, at the end of the day, it will not be so difficult to solve it, but at first sight, it looks a bit hopeless because you would maybe want to do something like a Picard iteration. This. So this would be maybe a natural approach to try to solve this equation with the Picard iteration. But then the problem is that this guy here is losing you regularity in the n variable and then inverting this L0, which you can do. This is a nice symmetric operator. This is like a Laplacian. So this you can invert, but it's not gaining you back the loss in the n regularity you have here. And so you cannot run this Picard iteration, right? So after one step already, basically you're out of your space. And also, depending on what your alpha is, it could be actually that this 1 minus 3 over 2 alpha is actually losing more than one order with respect to this L0. So if the alpha is less than 3/4, you lose too much even to gain back the L0 regularity. Yeah, but we, in this picture, if we see it like that, we don't really use the structure, right? So I said the important part here is that the G is antisymmetric or sufficiently close to antisymmetric. And this will give us some free energy estimates. And based on these free energy estimates, we'll get our first construction of the semigroup. Formally or rigorously if you have enough regularity. Because this thing, so I said G star is equal to minus G, so this would be, right, like this. And that's of course the same expression, so it has to be 0. And so what you do is approximate this by a scale of operators Gn, such that Gn is bounded, let's say for all n. And we have the same property. And maybe just as a remark, then I can say that once, and after that not talk about it anymore. What really would suffice here would be some estimate like that, which is the usual estimate that you have for like energy methods for SPDEs. So you need that the kappa is less than 1 and the lambda can be in R. So that means somehow that in the sense of energy, this operator G can be seen as a perturbation of the symmetric part. You know? In terms of regularity estimates for G naught, it's not a perturbation, like never, because it always loses n regularity and L0 can never regain n regularity. But in terms of energy estimates, it's a perturbation. That's some of the critical point. And that's always given if it is anti-symmetric, because then you just get 0, and 0 is, of course, bounded by the right-hand side. Yeah. So we have this, and then we look at 1 minus Ln by n is equal to psi, let's say for some psi in h minus 1, 0. And okay, just testing. I will not give the argument, but it's like a 1 or 2 line argument. We get this bound. So the solution to this equation here is bounded by the right-hand side uniformly in n, no matter what the GNs do. Like at this point, this doesn't depend on alpha or anything. Yeah? So this is always true. It's just using this factor. And it's a one-line argument. This means we can define somehow this operator. This converges weakly along a subsequence. To some R1 in linear operator from h minus 1, 0 to h1, 0. And this is weakly in L. So in this, okay, in the same space. Okay, but this works for any such sequence of operators G, right? So I could, for example, take like some Gräfner truncation of my G, but now not take the truncation away, but just multiply this thing with larger and larger numbers. We would get the same estimates uniformly in N. So like at this point, using only the structure we had, there's no reason to believe that the limit would satisfy any nice properties. But now we look at the estimates that we have for the G up there. So if G maps H10 to somehow H minus infinity infinity, which we just define as something like that. So any space that you want, basically, then one gets from this weak convergence and like a bit of processing, you get that 1 minus L R1 of psi is equal to psi for all psi in H minus 1, 0. So now in this case, we get that the limit that we constructed here solves the resolvent equation. We solved the resolvent equation. We constructed a solution to the resolvent equation. And so we can get a domain. Let's call it like this. Okay, we want at the end, we don't want to map to distributions, but to something of regularity 0. So let's say we take the right-hand side only in H00, and then we get a domain. So now we have an operator and a domain, and from this, with some general functional analysis result, basically we get that we have a semigroup because so let's say easy to see. Another 2-3 line argument. This is dissipative. This means we have such a bound. And then there's a general result from functional analysis, Luhmann-Phillips theorem, like a version of Hilo-Yoshida, which tells you whenever you have a linear operator which is dissipative, such that you can solve the resolvent equation for any right-hand side, so for which the resolvent is surjective, then the operator generates a contraction semigroup. So we get a semigroup in that case. I think like this. Of course, somehow everything at the moment was extremely soft, and so there's not really any reason to believe that anything should be unique, but we found a semigroup attached to this operator at least. The operator is defined without reference to any of these constructions, right? So the G is given from the equation. I didn't build anything to define the G. The G is defined whenever I plug in something in H10, let's say. It's just that the right-hand side in general then has very bad regularity. But the G is always given. The L0 is also always given. The only thing that we really constructed was the domain. And then from the domain, you get the semigroup. But it could be that another construction would give you a different domain. And in general, I think it will, and this abstract framework. But still, this gives you a Markov selection. So a Markov process with a semigroup given by that for the fractional burgers with alpha bigger than 1/2. 3/4 is critical. And for the surface quasi-geostrophic, we need alpha bigger than 0, and alpha equal to 1 is critical. And for the SDE with divergence-free, we have B in h-1 plus epsilon. Okay, and then critical depends a bit on integrability here, and so maybe I don't say what is critical here. But in any case, this is very, very supercritical. Okay, now I still have 10 minutes? Okay. Yeah, so the last part is to get the uniqueness, which is really the newer result here. So some of this was very, very soft, didn't use many properties. Now the point is if we use one more ingredient, then we will get uniqueness of the semigroup and uniqueness of energy solutions of the martingale problem, which is defined without reference to the operator, if that tells you something. But, or if we just talk about the operator, it gives us uniqueness of the domain and therefore uniqueness of the semigroup. So here maybe stress that this depends on d tilde L. Yeah, so how do we?
So what makes critical critical? Because you have the results for
yeah.
Critical, but where can I see some changes?
In the uniqueness, you will see it. So uniqueness will accept in this case where somehow there's more structure that you can exploit. In these cases where we stay in the Hilbert space world, somehow we will need criticality to get uniqueness. We will need some control of G by the L0 in some weak sense. So the G should not dominate the L0. While here the G could dominate the L0, you don't really see that in this whole story. So for the uniqueness base, I mean, yeah, you will see, but basically this stops working if you don't. Okay, how do we get uniqueness? The natural domain for the operator would be d of L this is the simplest thing you can think of, no? So these are all phi and H10. So the L is defined on H10, it's just mapping to a horrible space in general. But it's defined for any such phi, and you just look at all those phi's for which it is back in your space. And that's like the maximal domain. Like you cannot take anything bigger than that, and that would be the best domain you can hope for. And so if we show that this d tilde L, independent of the construction, independent of the subsequence we took, is equal to this, then I define the operator on the maximal domain. It generates a contraction semigroup on this maximal domain, and therefore this semigroup must be unique. So we just have to prove this. And this follows. So let's record this. If d tilde L is equal to d of L, then we get that. Yeah. And if 1 minus L on d tilde L is injective, So, okay, let's clear what that means. Then we have that R1 of 1 minus L then we can take such a phi in the maximal domain. And if we take such a phi in the maximal domain, then this is an element of H00. So this here is in my d tilde L. And now I can apply 1 minus L to it. But this thing here is the identity always by construction. And this is equal to 1 minus L phi. And this operator is injective. So from that, we would get that R1 1 minus L phi is equal to phi, because they both have the same image under this map, right? So this guy here and this guy are mapped to the same element, but this is an injective operator, and so they two have to be equal. And so therefore, phi is in d tilde L. And so once we prove the injectivity, we have the uniqueness of the semigroup. And now we just need to get the injectivity, and for that another observation. If phi L phi is equal to, so let's see formally what this should be. And maybe I want here actually it doesn't matter so much, but so this is what I would expect just by formally doing using the anti-symmetry here. The problem is that to say that this phi g phi is equal to 0, the g of phi should be in the dual space of this phi, which is not guaranteed in the setting we have. Yeah? So formally, I can do some of this integration by parts to see that I should get this, but rigorously, I cannot do it under the regularities that I have. But if I could justify that, so this is what I want to get. Then we're done, because then if 1 minus L maps something to 0, then the left-hand side is 0, but then the right-hand side is 0, and then phi is 0. So if we can justify this identity, again, then we're done. So it comes down, the whole problem comes down to justifying this identity. And there we need, well, first of all, better regularity of G, and then a commutator estimate, a trivial commutator estimate. So how do we get this? So this has to be for all pi in tilde L. Yeah. We assume that this number operator and G, well, they don't have to commute, but the commutator of here we can put beta minus 1, actually minus 1. Beta can be 0. No, let's put 0. H1. 1. So recall before we had something like G of phi H minus 1. Okay, and then we had this 3/2 alpha. And here we had 1/2, which was linked to the quadratic nonlinearity. If you would take cubic, there would be 0 here. And then H1, 0. So if alpha is 3/4 or bigger, then you have this estimate for G itself. But now here we require basically, so this we have for G if alpha is bigger or equal than 3/4. And so here you see also this control now really of G in terms of the L0, because we can only lose now 2 degrees of regularity in L0, which means somehow exactly 1 power of the operator L0. Yeah, so we have this estimate. And now what is this commutator estimate? Well, then you use, in this specific case, that the G is actually just permuting the chaos by going up 1 or down 1. And so it nearly commutes with the number operator. So the commutator between them is somehow bounded by G itself. So the commutator satisfies the same bound as the G itself. And that's why we get this. If alpha is bigger or equal than 3/4, with a quadratic one and with a cubic nonlinearity, you would still be able to handle the lower regularity here, but then also things would change up here and so on. For cubic, you would need alpha bigger than 1. Right, and with this, so let me just one more line. We see that, so we have to prove this identity here. And so we take the phi like this, and at lambda going to infinity, lambda squared lambda plus n to the -2 . So this is just dominated convergence here. Well, there's nothing happening here. But now I regularized somehow. I have this, I mean, as lambda goes to infinity, this thing just converges to 1. No? But now I regularized in n. Now I can do the integration by parts. And then I want to use the anti-symmetry of the G. But the G now with respect to this new inner product is not anti-symmetric, but nearly, because we have this estimate on the commutator here. And so through that, with applying dominated convergence 2 or 3 times, we get that indeed this is equal to this, and with that, we're done. Okay, then there's this other part, like the more probabilistic part of the story, and you want to connect these two, and so that I didn't speak about now, but at least the functional analytics side of the story now is done. So we have shown that the domain is really the maximal domain. Therefore, the semigroup that we construct is unique. And so therefore, this operator generates a unique contraction semigroup, which is also a Markov semigroup. So just we have this here for that's just the examples, last thing. So for burgers, we now need this alpha bigger than 3/4, bigger or equal to 3/4, and 3/4 is critical. And for the surface quasi-geostrophic, we need alpha bigger than 1. So there's a big gap between alpha bigger than 0, where you get the semigroup, and alpha bigger or equal to 1, where you get uniqueness. Okay, and the finite dimensional case is more subtle because there are other things coming in, so I won't comment on that. So let me stop here. Thanks.